Welcome back, aspiring cybersecurity professionals, to episode 12 of our comprehensive cybersecurity course. I'm your instructor, and I'm thrilled to continue our journey into the fascinating and critical world of web application security. In our previous episodes, we laid the groundwork for understanding the Internet, network protocols, and the fundamental components that make up our digital landscape. We've explored topics ranging from cryptography to network defenses, building a robust foundation for identifying and mitigating threats. Now, we're diving deep into the intricate realm of web applications, those interactive platforms and services we use every single day. Today, we confront one of the most pervasive and dangerous vulnerabilities that has plagued web applications for decades: SQL injection. This isn't just a theoretical concept. It's a real-world weapon in a hacker's arsenal, capable of breaching databases, stealing sensitive information, and even compromising entire systems. By the end of this episode, you'll not only understand what SQL injection is and its various forms, but also how attackers exploit it, how to identify these vulnerabilities, and most importantly, the robust techniques developers must employ to prevent them. Get ready, because we're about to uncover how hackers break databases, and more importantly, how we can stop them. Before we delve into the specifics of SQL injection, let's quickly recap some foundational concepts crucial for understanding this attack: databases and SQL. At the heart of almost every dynamic web application lies a database, a structured collection of information. Think of it like a highly organized digital filing cabinet. Within this cabinet, data is stored in tables, much like spreadsheets, with rows representing individual records and columns defining the attributes of that data. For instance, a user's table might have columns for username, password, email, and user_ID. To interact with these databases, to retrieve information, add new records, update existing ones, or delete old ones, we use a specialized language called SQL, which stands for Structured Query Language. SQL is the universal communication protocol for databases. Commands like select are used to retrieve data, insert to add new data, update to modify existing data, and delete to remove data. When you log into a website, search for a product, or submit a form, behind the scenes, the web application is constructing and executing SQL queries to interact with its database. This interaction, specifically how user input becomes part of these SQL queries, is where the vulnerability arises. The fundamental premise of most web applications is to take input from users, process it, and often, use that input to query a database. Imagine a login page. You enter your username and password. The application then takes this input and constructs an SQL query, perhaps something like, select from users where username equals your_username and password equals your_password. The database then executes this query, checks if a matching user exists, and if so, grants access. The vulnerability arises when this user input is directly concatenated, or stitched together, into the SQL query string without proper validation or sanitization. It's like building a sentence based on someone's words, but instead of just using their words, you let them insert entire new clauses, or even completely different sentences, directly into your command structure. If a malicious user can manipulate their input to alter the original intent of the SQL query, they can trick the database into performing actions it wasn't supposed to, or revealing information it shouldn't. This critical flaw, this dangerous mingling of user data with executable code, is the essence of SQL injection. So, what exactly is SQL injection? At its core, SQL injection, often abbreviated as SQL, is a code injection technique used to attack data-driven applications, in which malicious SQL statements are inserted into an entry field for execution. The attacker exploits a flaw in the application's software, typically when user-supplied input is not properly filtered or escaped, allowing them to inject their own SQL commands directly into the query that the application sends to the database. The primary goals of an SQL injection attack are diverse and highly damaging. An attacker might aim to bypass authentication, logging in as an administrator without credentials. They could retrieve sensitive data from the database, such as usernames, passwords, credit card numbers, or proprietary business information. Beyond just reading data, SQL can also be used to modify, insert, or even delete data, potentially defacing websites, altering financial records, or destroying critical information. In some severe cases, depending on the database configuration and permissions, an attacker might even be able to execute operating system commands, effectively gaining control over the server hosting the database. Let's look at that login example again. If a developer builds a query like select from users where username equals, plus user input username plus, and password equals, plus user input password plus, and the attacker inputs, or 1 is equal to 1, into the username field, the resulting query becomes select from users where username equals, or 1 is equal to 1 and password equals, the characters are SQL comments, effectively telling the database to ignore everything that follows. Since 1 is equal to 1 is always true, the database returns all rows, allowing the attacker to bypass authentication entirely. This simple example highlights the profound impact of this vulnerability. SQL injection isn't a single, monolithic attack, it manifests in several forms, each exploiting different aspects of how an application interacts with its database. The first major category we'll discuss is in-band SQL injection, where the attacker uses the same communication channel to launch the attack and retrieve results. Within in-band SQL, one common type is error-based SQL injection. This occurs when an attacker intentionally triggers database error messages to extract information. Many database systems, when encountering an invalid or malformed SQL query, will return an error message containing diagnostic information. If the web application is not configured to suppress or sanitize these error messages before displaying them to the user, an attacker can leverage this verbose output. By injecting specific SQL functions that are designed to cause an error if certain conditions are met, or if a subquery attempts an invalid operation, the attacker can force the database to reveal details about its structure. For instance, an attacker might inject a payload that attempts to cast a string into an integer if a certain piece of information is true. The resulting error message might contain the database version, names of tables, columns, or even snippets of data. This allows the attacker to map out the database schema, step by step, by observing what information the errors reveal. It's like shaking a black box until something falls out, and that something gives you clues about what's inside. While sometimes crude, error-based SQL can be incredibly effective for reconnaissance and data extraction if the application is leaking these critical error details. Another powerful form of in-band SQL injection is union-based SQL injection. This technique leverages the union SQL operator, which is used to combine the results of two or more select statements into a single result set. The key requirement for a union query to work correctly is that each select statement must have the same number of columns, and those columns must have compatible data types in the same order. An attacker exploits this by injecting a union select statement into the legitimate query, intending to append data from other tables or databases to the original query's output. For example, if a web application displays products based on a query like select product_name, price from products where category equals electronics, an attacker might try to inject union select username, password from users, at the end of their input. If successful, and the column counts and data types align, the web page would not only display product names and prices but also, crucially, usernames and passwords from the users table, interleaved within the product list or appearing after it. The attacker first probes for the correct number of columns by trying order by clauses or a series of union select null, 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 until no error occurs. Once the column count is determined, they identify which columns display data on the page and then craft their union select statement to retrieve desired information from other tables within the database, presenting it directly in the web application's response. This method is incredibly effective for direct data exfiltration, as the data appears right on the screen. Now, let's explore blind SQL injection, a category of attacks where the attacker doesn't receive data directly in the application's response, unlike error-based or union-based attacks. Instead, the attacker infers the database structure and data by observing subtle differences in the application's behavior or response time. One prominent type of blind SQL is Boolean-based blind SQL injection. In this scenario, the attacker injects SQL queries that force the database to evaluate a true or false condition. Based on whether the condition is true or false, the application's response will differ in a discernible way. This difference might be as simple as the page loading or not loading, displaying a generic data found versus data not found message, or even just a slight change in the page's content or layout. For example, an attacker might inject an substring, @version 1 equals 5 into a query. If the first character of the database version is 5, the condition is true, and the page might load normally. If it's 8, the condition is false, and the page might show an error or a different output. The attacker then iteratively tests character by character, position by position, to extract information. They might test for the first letter of an admin's password, and substring, select password from users where username equals admin1 equals, then b, and so on, until the page behaves as if the condition is true. It's a slower, more painstaking process compared to in-band SQL, but it can be just as devastating, allowing attackers to reconstruct entire datasets without ever seeing a direct output of the data itself. Complementing Boolean-based blind SQL injection is time-based blind SQL injection. This technique is used when there are no observable differences in the application's content or behavior, or even explicit error messages, to indicate a true or false condition. Instead, the attacker relies on the time it takes for the database to respond. The attacker injects SQL queries that include a time delay function, such as sleep, in MySQL/PostgreSQL, wait for delay in Microsoft SQL Server, or similar constructs in other database systems. This delay is conditionally executed. For instance, an attacker might inject something like an if substring, select password from users where username equals admin1 equals sleep 0. If the first character of the admin's password is, the sleep 5 function executes, causing the database to pause for 5 seconds before returning a response. The web application, in turn, will take 5 seconds longer to load than usual. If the character is not, the sleep function is skipped, and the page loads quickly. By meticulously observing the response times, the attacker can infer the truthfulness of each condition they test. This method is even slower and more tedious than Boolean-based blind SQL, often requiring automated tools to be practical. However, it's a critical technique for extracting information from highly resilient applications that offer minimal feedback, proving that even a lack of information can be turned into a weapon in the hands of a determined attacker. Understanding the types of SQL injection is one thing, identifying them in real-world applications is another. For both ethical hackers and developers, knowing how to find these vulnerabilities is paramount. There are several approaches to uncovering SQL injection flaws. Firstly, there's manual testing. This involves systematically probing input fields, URL parameters, and HTTP headers with various SQL injection payloads. Testers will typically start with simple quotes, double quotes, or backslashes, \symbol, to try and break the SQL query, looking for error messages or changes in application behavior. They'll then progress to more complex payloads designed for union-based, error-based, or blind SQL, carefully observing the application's responses. This method requires a deep understanding of SQL and the different injection techniques. Secondly, automated tools are indispensable for efficiency and scale. Tools like SQLmap are powerful open-source penetration testing tools that automate the detection and exploitation of SQL injection vulnerabilities. They can identify the type of database, enumerate tables and columns, retrieve data, and even execute commands on the underlying operating system. Commercial web vulnerability scanners like Burp Suite Professional also include advanced scanning capabilities to automatically detect SQL flaws. These tools send a multitude of payloads and analyze the application's responses for patterns indicative of injection. Finally, for developers, code review is a critical preventive measure. By scrutinizing the source code, developers can identify where user input is handled and if it's being directly concatenated into SQL queries without proper sanitization or parameterization. Tools for static and dynamic application security testing, SAST/DAST, can also aid in this process by automatically flagging potential vulnerabilities in the code itself. A combination of these methods provides the most comprehensive approach to finding SQL injection vulnerabilities before malicious actors do. Preventing SQL injection is not just about understanding the attack, it's about implementing robust defenses at every layer of the application. The good news is that SQL is largely a preventable vulnerability, given proper development practices. Let's start with some foundational prevention techniques, though we'll cover the most critical ones in detail shortly. Firstly, input validation and sanitization. This involves carefully checking and cleaning all user input before it's processed by the application or used in a SQL query. Input validation ensures that the data conforms to expected formats, types, and lengths. For example, if a field expects a number, reject any input that contains letters or special characters. Sanitization, on the other hand, involves escaping or removing potentially dangerous characters from the input, such as single quotes, double quotes, or semicolons, that could interfere with SQL syntax. While important, relying solely on input validation and sanitization can be error-prone and is often not sufficient on its own, as attackers can often find ways around filters. Secondly, principle of least privilege for database users. This is a fundamental security principle. The database user account that the web application uses to connect to the database should only have the absolute minimum necessary permissions. For example, if the application only needs to read data, the database user should not have permissions to write, update, or delete data, let alone execute system commands. This limits the damage an attacker can do even if they manage to inject malicious SQL. And thirdly, web application firewalls, WAFs. A WAF sits in front of your web application and monitors incoming traffic for malicious patterns, including common SQL injection signatures. While a WAF can provide an additional layer of defense and block many common attacks, it's not a silver bullet. A WAF acts more as a perimeter defense, catching known attack patterns. It should be used in conjunction with, not as a replacement for, secure coding practices within the application itself. While input validation and WAFs offer some protection, the single most effective and recommended technique for preventing SQL injection is the use of parameterized queries, also known as prepared statements. This is the gold standard for secure database interaction. The core idea behind parameterized queries is to strictly separate the SQL code from the user-supplied data. Instead of building a SQL query string by concatenating user input directly, you define the complete SQL query structure first, using placeholders for any data that will be supplied by the user. Then, the user's data is passed to the database as separate parameters, not as part of the executable SQL code itself. Think of it like this. Instead of giving a robot a command that says, go to user's location and pick up item, you give the robot two separate instructions. First, go to location and pick up item, and then, separately, you tell it, location is user's location. The robot understands the command structure first, and then substitutes the safe, data-only parameter. With parameterized queries, the database system parses the SQL statement template first, identifying what parts are executable code and what parts are merely data. When the user's data is then supplied, the database treats it strictly as data, incapable of being interpreted as executable SQL commands. This completely removes the attacker's ability to inject malicious SQL code, as any special characters in their input are treated as literal strings, not as part of the query's logic. Let's delve a bit deeper into prepared statements, which are the specific implementations of parameterized queries in most programming languages and database connectors. The process typically involves 3 steps. First, the application prepares the SQL statement, defining its structure with placeholders. For example, in Python using SQLite 3, it might look like SQL equals select from products where category equals. The question mark here is the placeholder. Second, the database system parses and compiles this SQL statement template. At this stage, it understands the query structure, syntax, and what parts are meant to receive data. It doesn't yet have the actual user input. Third, the application binds the actual user-supplied values to these placeholders, sending them separately to the database. For our Python example, it would be cursor.execute, SQL, user_category. The database then executes the precompiled statement with the provided data. The crucial part here is that the database differentiates between the query's logic and the data values. It treats the bound parameters purely as data, regardless of what characters they contain. So, if a user tries to inject or1 is equal to 1 into the user_category parameter, the database will literally search for a category named or1 is equal to 1, which is highly unlikely to exist, and thus, no injection occurs. This robust mechanism is supported across virtually all modern programming languages and database systems, including Java, with prepared statement, C, with SQL command, PHP, with PDO, prepare, and many others. Developers must adopt parameterized queries or prepared statements as a mandatory best practice for any database interaction involving user input. There are very few legitimate reasons to ever concatenate user input directly into a SQL query. The theoretical understanding of SQL injection is essential, but it truly hits home when we examine its real-world impact. SQL has been responsible for some of the largest and most damaging data breaches in history, showcasing its devastating potential. One notorious example is the Heartland Payment Systems breach in 2008. This attack, primarily attributed to SQL injection, compromised over 130 million credit card numbers, leading to enormous financial losses, regulatory fines, and a significant blow to the company's reputation. Another significant incident involved Sony Pictures in 2011, where hackers used SQL injection to access personal information of over 1 million users, including passwords, email addresses, and home addresses. This breach not only exposed sensitive customer data but also resulted in the leak of internal documents, severely damaging Sony's brand image and leading to costly remediation efforts. More recently, in 2015, the UK telecommunications company TalkTalk suffered a major data breach, also attributed to SQL injection, which exposed the personal and financial details of over 150,000 customers. The CEO later stated the attack cost the company an estimated £60 million. These incidents are stark reminders that SQL injection is not a niche vulnerability, it's a persistent threat that can lead to massive data exfiltration, financial ruin, legal liabilities, and irreparable damage to a company's reputation and customer trust. The sheer volume of sensitive data that can be compromised, from financial records and intellectual property to personally identifiable information, underscores why secure coding practices, particularly the use of parameterized queries, are not just good practice, but an absolute necessity in today's digital landscape. We've covered a tremendous amount of ground in this episode, dissecting one of the most critical web application vulnerabilities. Let's consolidate the key takeaways. First and foremost, SQL injection is a dangerous code injection technique where attackers insert malicious SQL statements into user input fields, manipulating the database's intended operations. We explored its various forms: in-band SQL, which includes error-based SQL injection, where attackers infer information from verbose error messages, and union-based SQL injection, where they combine legitimate and malicious select statements to extract data directly onto the web page. Then, we delved into blind SQL injection, which comes in two primary forms: Boolean-based blind SQL, where attackers deduce information by observing subtle true/false responses from the application, and time-based blind SQL, where they infer data by measuring deliberate delays in database responses. We also touched upon how these vulnerabilities are discovered, through both manual probing and automated tools, as well as critical code reviews. Crucially, we emphasize that prevention is not only possible but mandatory. While input validation, adhering to the principle of least privilege, and utilizing web application firewalls offer layers of defense, the ultimate and most effective countermeasure is the adoption of parameterized queries and prepared statements. These techniques fundamentally separate SQL code from user data, eliminating the attack vector by ensuring that user input is always treated as data, never as executable commands. The real-world incidents we discussed, like the breaches at Heartland Payment Systems, Sony Pictures, and TalkTalk, serve as powerful reminders of the catastrophic consequences: massive data breaches, severe financial losses, and irreparable damage to reputation that can result from neglecting this critical security measure. Protecting our databases from SQL injection is a non-negotiable aspect of building secure web applications. And there you have it, a comprehensive dive into the world of SQL injection. You now possess a deep understanding of how this attack works, its different manifestations, and critically, how to protect against it. This knowledge is invaluable for anyone aspiring to build secure web applications or to defend them against the relentless tide of cyber threats. I hope you found this episode both enlightening and empowering. But our journey into web application security is far from over. While SQL injection attacks the back-end database, another equally prevalent and dangerous vulnerability targets the front-end, the user's browser itself. In episode 13, we will shift our focus to cross-site scripting, or XSS attacks, the client-side threat. We'll uncover how attackers inject malicious scripts into trusted websites, tricking browsers into executing them, leading to session hijacking, defacement, and a host of other client-side dangers. It's another crucial piece of the web security puzzle you won't want to miss. If you found this episode informative and valuable, please hit that like button, subscribe to the channel for more in-depth cybersecurity content, and share this video with anyone who could benefit from this knowledge. Your engagement helps us reach more aspiring cybersecurity professionals. Also, I encourage you to leave your questions and thoughts in the comments section below. I love hearing from you and engaging in discussion. Thank you for being a part of this cybersecurity course. Stay curious, stay vigilant, and I'll see you in the next episode.